This lesson is for FST, lesson 10.4 on probability distributions. Students, you will need a graphing calculator for some of the questions in this lesson. A probability distribution is a function that maps each outcome or event onto its probability. And we'll see an example of this shortly. Every probability distribution has three characteristics that students need to be aware of. The first one, the domain, is the set of mutually exclusive, which means no overlap, mutually exclusive outcomes whose union is the sample space of the experiment. Again, remember that sample space covers all of the outcomes. A probability distribution also maps each outcome or event onto its probability, so the range is the set of probabilities. And then the sum of those probabilities, or the entire probability set added together, has to be 1 or 100%. So let's see a familiar example. This is given to you in your textbook. The problem would have started out by identifying x as your random variable, and the variable is finding the sum of two dice. So I indicated the outcomes here with a picture. And so let's go through now and find out those sums. If you add the first two dice together, you get 2, the next one you get 3, and so on. And then let's keep going. And so now you can see that the sums have all been indicated here. So the x's are all the different outcomes that result when you add up the two dice. So clearly the smallest sum you can get is a 2, and the largest sum we got is a 12. So I listed out those outcomes from 2 to 12. You can't see the bottom ones, I'll scroll down later. Then the y values, or the range, is going to be the probability of each of those. So for that, you just count up how many of those there are. There's only one outcome with a 2, so that's 1 out of 36. There are clearly two outcomes that have a 3, so that's 2 out of 36. One piece of advice here for students is leave all of your probabilities with the same denominator for your table. It'll make it easier to graph later. But know that when you're working with a quiz or a test, you should also provide all of these fractions either in decimal form or as fractions in lowest terms. But in terms of you moving forward, most of the time the probabilities will be easier to deal with if you keep all the denominators the same. So here's the rest of the table here all the way down to 12 with, again, the probability there being 1 out of 36. Just to verify the characteristics, if you were to add up all of these probabilities, you'd end up with 36 out of 36, which would indeed make a 1. Now let's go ahead and graph this table. Students may or may not be asked to graph. If you are, you can make the graph as simple as possible. Just label what your event is, so in this case the sum of two dice, and the outcomes for the domain were from 2 to 12, so I went by 2's here. And then for the probability, notice how you don't have to get real fancy or complicated here. I just went from 1 out of 36 for my first chunk all the way up to 6 out of 36, so I was able to label it based on the numbers that I was given. If you would prefer to do this in decimal form, you're more than welcome to do it that way. So your x's are the outcomes and the y values are your probabilities. And so you can see here that this particular graph has a nice pattern to it, and it's pretty obvious that the one that happens the most often, or the average sum of the two dice result, is clearly up here at the highest value, but the actual answer to that question would be the 7. 7 occurs most often, and so that is the average, or the average sum. Not all the graphs are going to have that shape to it, but know that in a sum of two dice situation, you're always going to get that shape. So that's a typical probability distribution situation that students will have to encounter. They'll be given a situation, they'll set up a table, they'll determine the probabilities, and then potentially maybe graph them. So let's talk more in depth about this random variable that we're working with. Now that we've got a random variable like the one we just did, like the sum of two dice, you may be asked to calculate mean, and then later on in this lesson we'll look at variance and standard deviation as well. When we talk about a mean, it's not just a regular mean, it's the mean of a random variable. So know that this whole statement goes together. So you'll always see that phrase as opposed to just the mean. So let's read what the book says about this information. Back in chapter 1, you studied the standard or the regular average or the mean, which we called x bar. Why do we need the mean of a random variable then? In the calculation of a regular or a standard mean, all values are given the same weight. In contrast, however, the mean of a random variable x is a weighted average of the variable where the weights are the probabilities. So you can see back on our previous example, our variable was the sum of two dice. In this case, it was an x. And the probabilities mean that some of these outcomes are more likely than the others. So that is why we want to use a weighted average. Let's continue to read what the book says. The critical difference between a standard mean and the mean of a random variable is that all elements of that data set are not necessarily equally likely, so it's not necessarily given the proper weight. A common example is a lottery. Some of you are probably not old enough yet to play the lottery, but you're probably familiar with what it means to play. A lottery is in which a random 4-digit number is picked, pays out $8,000 to the winner. There are 10,000 4-digit numbers that are handed out. So then the probability of winning is 1/1000th, or 0.0001. If we let the random variable x be how much you win, then the probability distribution can be organized in the table at the right. Notice that this table is much smaller. It's also horizontal instead of vertical like on our previous one. The x is how much you win. You either win nothing or $8,000 when you play. And the probability is either 1/1000th or its complement, 0.9999. So there's only two outcomes here, so our table is very small. On our previous example, we had a lot more outcomes, so we had a much larger table. So now let's talk about the unweighted average, or just the regular average here. You either win nothing or $8,000 out of the two outcomes, so the average winnings here would be 4,000. However, we know that this doesn't make sense because you know that a player is much less likely to win $8,000 than they are to win no money at all. In the long run, let's say after all 10,000 tickets have been sold, you would therefore expect to win 8,000 only once and win nothing the other 9,999 times. So therefore, in the long run, your average winnings from a ticket would be the weighted average here of 8,000 times 0.0001 plus 0 times 0.9999. So therefore, the weighted average is 80 cents. And that's a significantly different result from the unweighted average of $4,000. We still would not say that we're more likely to win 80 cents each time, but that's a more accurate depiction as opposed to the 4,000. The mean of the random variable here is denoted by the Greek symbol called mu. It's also used for the mean of a population as we did back in chapter 1. The following generalizes the situation for any probability distribution. So this is one of those very important yellow boxes that's listed in the book, and it's the definition of the mean of a random variable. Keep in mind, students, that this is also sometimes referred to as the expected value. So you'll use the same formula for both. So it's pronounced mu, and it's this curly Q looking letter M, and it's for the mean of a random variable. You're going to take the sigma, which hopefully you remember means the sum of all the x's, which is the outcomes, times their probabilities. So basically you're going to take the sum of the outcomes times their probabilities. That's all it means. Keep in mind here that the i's didn't really turn out very well on the reprinting here. So know that this is I equals 1 as the sum goes from 1 to n of x sub I times its probability of x sub I. So let's see this formula in action. And this example is from your textbook. It's example 1 from page 639. So if you don't like my explanation, you can always refer to your textbook here. In the card game of bridge, a standard 52 card deck is used. That deck has 13 cards in it, each of 4 suits, and those are labeled here if you're not familiar with a deck of cards. In the game of bridge, the deck is distributed randomly among only 4 players, so it has to be a 4-person game. Because certain cards beat other cards during the game, it is common for a bridge player to evaluate the 13 cards in their hand according to the following scheme. An ace is worth 4, king is worth 3, queen is worth 2, jack worth 1, and all other cards, the cards from 10 to 2, are all going to be worth nothing or 0 points. So let x be the random variable that represents the number of points a card is worth, and we're going to make a table representing the probability of those. You can make your table pretty much any way you'd like. I'm going to do a horizontal table here because that's what I have room for. So remember that the tables are always going to look pretty much the same. They're all going to start out this way, as with your x's and then the probability of the x being the y value. So we have to think about what are the x values. The x value is the number of points a card is worth. So they tell us that information in the question. An ace is worth 4, king is worth 3, queen is worth 2, jack is worth 1, and then the rest are all worth nothing. So that means all the outcomes are between 0 and 4. So then what's the probability of each of those? Let's start with the 4 since that's mentioned first, but know that you could list out whatever you'd like. So I'm going to do aces are worth 4 points. I know that there's 4 suits and that there's 4 aces in a deck, so I'd say 4 out of 52 here. The same thing is going to be true for the king, the queen, and the jack. Those are all 4 out of 52 for their probability. So then that helps me determine how many cards are worth 0. So if there's 4, 8, 12, 16 cards that I've already accounted for out of the 52, I do 52 minus those 16, that gets me 36 out of 52. So from here, you may or may not be asked to graph these outcomes. We're just going to go ahead and keep answering what they ask us. They don't ask us to graph, so we're not going to bother graphing. Part B here asks us to calculate the mean of that random variable, so we're going to go ahead and utilize the formula. Remember that the formula asks you to add up the x's times their probabilities. So we're just going to show that here. So I take the first outcome, which is 0, and I multiply it by its probability, 36 out of 52. Now I'm going to add that to the next outcome times its probability. Now the bad news here is, folks, there is no shortcut for how to do this on the calculator. You simply have to type it in. I'm having you copy it now because you'll want it as a visual reference in your notes. But know that you could technically just go right into typing this in on your calculator rather than having to write it down. So I just took each of my elements in my table and I multiplied the top number by the probability below it, and then I added it to the next one. Now think about it though, you can save a little bit of time here when you type it in on your calculator. I'm hoping that you know that you shouldn't type in 0 times 36 over 52 because we know that that's simply going to become 0. And we wouldn't really need to write 1 times the probability here, so you're really just going to start typing right about here. And so you're really only going to type in this portion. And when you're done typing all of that in, if you typed it in carefully, you should get either 10/13 or in decimal form about 0.769. And so here you would round to whatever they asked you to. So that is the mu, or the mean, of the random variable x. So that is for question B there, and our table here was for A. And then for part C, they ask us to find the expected value. Know that expected value is the same as the mean of the random variable. Those are the same thing, just a different name. So you would say same as B. Now for question 9, we use the same information, but we're going to find the variance in the standard deviation. We will come back to that after I've shown you what the variance is. The book gives you 2 definitions for variance, and I've listed them both for you here. The first definition that they give is listed here. I have added in some additional brackets. Then they also give you an alternate formula, and that is the one that I'd prefer students use. It is much easier to handle and much easier to remember. There will be slight differences in the calculation itself, but for the most part you do get the same answer. So notice on the first definition you're still going to be doing a sum, and all these little subscripts here are still the letter I. Notice that mu appears in the formula for variance. So if you don't know the mean of the random variable, you are not allowed to calculate variance. You need to know the mu first. So the original formula had you taking each x, subtracting the mu from it, that's called a deviation, and then squaring it, and then multiplying it by the probability, and then adding it to the next one. That became quite tedious and quite of a lengthy computation, so they did a little math on this and reworked it a little bit. And so that's where this formula comes from. Here you're going to take the x's and square them, then multiply by their probabilities and add them up as you go. Then you're going to take away mu squared at the end. So let's try that formula, the easier one, on the previous question. So for 9a, we're going to take the same answer as what we did for the example part B. So I'm just going to copy and paste that. But you're going to have to make sure that you square all the x's. So that's the same answer as what we had before for mu, only now the x's get squared. We still multiply by the probability, we still add as we go, and then when we're all done, we have to take away mu squared. So it's a fairly simple formula for variance. It's almost identical to the mean, except that it's got the x's being squared, and we have to take away a mu squared at the end. So remember what we got for mu? We got about 0.69, and we have to square that. So when you calculate here, you should get about 1.7 approximately, and that's for 9 part A. And then for part B, hopefully you remember how to find standard deviation once you have variance. The square root of the variance is the standard deviation. Hopefully you already knew that. So we would take the square root of our answer from part A to get the standard deviation, which in this case is about 1.3. There is another good book example on page 640 and 641. It's book example 2. I'd recommend students take the time to go through that example on their own. As a final note, I would recommend highly that you do questions 8 and also number 11. And if you need help with those, make sure you talk to your teacher. I've provided for you here what question 8 looks like, as well as the dice which you'll need for both number 8 and number 11.